So we'll make a transition here into two-sample testing. First thing we'll look at is um, two-sample means. So the idea here that we'll look at two-sample mean tests. So some of the details about a two-sample mean test. We're actually going to end up comparing one group to another. So some of the notation for this, right, a population mean associated with the first one would be mu1. And the standard deviation for population for the first group would be sigma 1. And then if we're talking about a sample group, that'd be x bar 1 and s1. So in order to denote that we're talking about the second group, we'll use mu2 if it's a population, sigma 2 for population, and then x bar 2, s2. That's just some standard notation so we can tell the difference between the groups. Hypotheses, a lot of the rules stay the same. So our HO here, still going to use the same symbols of equals, greater than or equal to, less than or equal to. However, now we're going to be comparing two different groups. Or we're going to try to see, is there a difference between two populations? So now we're going to have mu1 and mu2 in here. All right, so same deal for alternative. We've got the same um, inequalities and equalities. Um, not equal to, all these things still go with their assigned hypothesis. It's just now instead of comparing one population to a given number, we're going to compare one population to another. So let's take a look at one example here in July 2007. Here's this Consumer Reports on two kinds of hot dogs, a meat hot dog and an all beef hot dog. So the researchers got several different brands and they found the average calorie count for meat was 111.7 compared to 135.4 for the beef. So they're interested, is there a difference? So one of the differences between the one sample test and two sample test we're going to do now is let's go ahead and identify the two populations. There's not a hard and fast rule to this. My thought is meat came first in the sentence, so we'll call meat first there. And since it comes second in the sentence, we'll call this the, the beef hot dogs, right? So set up the hypotheses. So we got HO and HA. We are talking about means throughout this entire presentation. So we're going to compare mu1 to mu2. So here, is there a difference? That's leading me down the road of not equal to versus they're the same, right? So either the two averages are statistically equivalent or there's a statistical difference. One more example here. So this Common Core is an innovative approach to teaching math. So they do a field test in 36 high schools over a 3-year period. And they're going to compare performances to Common Core with traditional. So there's population 1 will be CPMP. Population 2 will be traditional. And then we've got HO. We're going to compare two means. And then HA, again, comparing two means. And this time, researchers are interested if there was improvement with CPMP. So in other words, will population 1 be greater than population 2 in this case? And the null here can just be that there is no difference between the two curriculums. Okay. So here are the new conditions, or slightly altered conditions. Because we have two sets of data, we need each of them to come from an SRS. Because there are two sets of data, we need each to be normally distributed, or that n1 is greater than 30 and n2 is greater than 30. So either, they're both from a normal distribution or they're both big enough. And then finally, that both groups are independent of each other. We just want to make sure that there's not an overlap. So really, it's a matter of kind of thinking through the process to think, does one group affect the other group? We think back here, the Common Core versus the traditional, one curriculum is not going to affect the other. Those are independent. The hot dogs, a meat hot dog isn't going to affect an all beef hot dog. So for us, something that might not be independent would be a pre-test and a post-test, right, done on the same person. There's this one could affect the other because, well, it's the same person taking the test. Another example maybe if it's We did this early in the course. We do something on the left and right foot, right? We put waterproofer on the right foot and or shoe on the right foot, and then nothing on the left foot. And we're going to compare it. Well, those two aren't independent because they're on the same person, right? So one could obviously affect the other. The test statistic here, just like we've been doing, observed minus predicted over standard deviation. This is not going to be new. Um, you might also see it written as statistic minus the parameter over standard deviation of the statistic. So here, it looks kind of big and scary, but it's not really all that bad. Here's one thing. We were looking for a difference, right? We're testing for a difference. This is one way that I remember what's happening with your test statistic in terms of setting it up. So if we're testing for a difference, another word for difference is subtraction. And sure enough, what pops up all along the numerator is subtraction. This denominator, if you go back to some of the early stuff in the course, you remember that we never subtracted standard deviations. We always added those together, and technically we never added standard deviation. If you remember back to about unit 3 or 4 in this course, we talked about you always convert standard deviation to variance. Remember, standard deviation squared was the variance. So that's what they're doing down here in the bottom. They're converting everything to variances, and you always add the variance, right? When we combine two distributions, there's always going to be more variation. So one other thing to realize, we'll take a look at this piece right here. Well, if you go back to typically your HO is mu1 equals mu2. If we move everything to one side, mu1 minus mu2, which I think that's the same thing we have here, well, that equals 0. So really, we're going to work under the null hypothesis that really there is no difference between the two groups. So a lot of times what ends up happening is this number right here becomes 0. Now x bar 1, x bar 2, those will usually, they're not going to be 0 because you're going to get two different means from two different groups. So what's happening though with this when you're subtracting the parameters or the predicted values, so mu1 minus mu2, that's always going to be 0. So at the end of the day, it kind of cleans this test statistic up a little bit, that really you just have x bar 1 minus x bar 2 over that crazy looking standard deviation. Now, if it's a t-test, the degrees of freedom here are kind of hard to calculate. We're going to let the calculator take care of it for us. And then, should you be doing a two-sample z-test, it's really going to be much of the same, x bar 1 minus x bar 2, and then really it's minus 0. And your standard deviation now would just be sigma 1 squared over n1 plus sigma 2 squared over n2, right? So the only difference to a z-test is sigmas instead of s's. So let's do one quick example. So here's an example, some research done by the University of Newcastle about coffee station and voluntary collections. So they alternated pictures of eyes looking at the viewer and flowers looking, and then it's an honesty box where people would put in contributions depending upon how much milk or food they took from the coffee station. So really what they're taking a look at is, are people more honest if there's this perception of people watching them? So what they've done, this is kind of a weird statistic they come up with. They've somehow come up with this number that incorporates how much consumption there was as compared to the contributions per liter of milk. So it's kind of a weird looking thing, but one thing we can tell, it looks like typically eyes, right? Typically eyes a little bit bigger than flowers. There's more, right? There's typically a higher value of contributions. However, one other thing to look at, if you look at spread, the one with eyes is also more spread out. So even though it looks like it's higher, it might not be all that significant because it's much more variable. There's much more variation in the eyes. So let's run a two-sample test to see. One thing to realize, they give us S, not sigma, so we're going to run a two-sample t-test. And then down here at the bottom, kind of hard to see because of this, but they're looking, is there a difference? So researchers are interested, is there a true difference? So they're looking for a difference, so really that's equals versus not equal. They don't think that one's bigger than the other. Let's just see if there's a difference between the two. So let's run the test. So like I said, this is a two-sample t-test. Degrees of freedom here, it's a little bit complicated, so we'll make note of it. We're going to let the calculator do the work. We'll come back and fill that in a minute. HO was that mu1 equals mu2, and HA, that mu1 was not equal to mu2. Now let's just make a quick note here that population 1, we'll call that eyes, and then population 2 will be flowers. All right. Quick check over here. I'll just run my conditions off to the side. They both need to be from an SRS. That wasn't given, so we're going to assume it. They were both small. I think both were sample size 5, so we're going to have to work on the assumption that both are coming from a normal distribution. So we'll assume that as well. And then here's the one additional thing that we need to throw in here with two samples. We need to make sure that they're independent of each other. And here, think about that for a minute. A picture of flowers is not going to affect a picture of the eyes. So looks like we're good to go. So I do want to make note of this, so I make sure I come back and fill it in. So it's a two-sample t-test, which means we have a test statistic of t. You kind of go back and forth. So x bar 1, 0.417 minus x bar 2, 0.151 minus that mu1 minus mu2 will always be 0. And then we go 0.1811 squared over 5 plus 0.067 squared over 5. And it's at this point, I'm going to let the calculator take over for me. There's a two-sample option in there, two-sample t-test. I'll plug all my values in, and you will be asked, do you want to pool? And for us, that answer as of now is always going to be no. Eventually, we'll show you how yes works, but as you're doing this in the calculator, you're going to eventually be asked, do you want to pool the data? Or it'll just say pooled, no or yes. Select no, calculate everything. We end up with a test statistic of 3.08, a p-value of 0.026, and right below that, there it is, my degrees of freedom, 5.07. All right, so we will use alpha. It didn't tell us. We'll just go with the old standard 0.05. So 0.026, less than 0.05, which leads us to reject HO in favor of HA. So in other words, we now think that this is what the evidence is telling us. So evidence suggests that the average giving for eyes is not equal to average giving for flowers. You might also say, you could also say there appears to be a difference, right? There appears to be a difference. Here's another way you could look at it. Another way you could have written this one. Sorry, I'm running out of room. Really hard to write in the corner. Let me see if I can clean that up just a little bit. But another way of looking at this, since we're looking at HA as being the truth, or what we think is the truth, we could go ahead and say that if they're not equal, then there is a difference. Right? It's just another way of saying it. So there's a two-sample t-test.